We have a joint meeting sponsored by multiple societies in IEEE Silicon Valley, SSCS, CAS, CS, SCS, and CIS. We'd like to thank all of our sponsors. To introduce myself, my name is Mustafa Sharifzadeh. I serve as chair for the SSCS Society this year, and we are very glad to have you for this joint seminar tonight. So let me somehow the slide doesn't work. Could you go to the next one? Yeah, hopefully it works when the speaker starts. Yeah. Okay. Could you manually just move forward? It's not working? No, it's working. I mean, I can't see the LED. Could you just do it manually yourself? So just a couple of announcements for the future talks that we're planning with the sponsoring society. Still we are in planning mode for the SSCS, but the signal processing, they've already had some, yes, thank you very much. We'd like to thank all of our sponsors. Special thanks goes to our venue sponsor, Texas Instruments. Let's have a round of applause for Texas Instruments for sponsoring this fantastic venue for IEEE, all IEEE societies in Silicon Valley. I think they sponsored up to 10 societies. So those, some introduction of IEEE Santa Clara Valley, and you've already seen those slides during the networking session. I'll just go through them very fast. We have a lot of activities. The main thing, you can find all of the information for local activities at egris.biz. On Egris, you can subscribe and get the emails, also see all the events, local events from all, I think, 40, 50 IEEE societies in the valley. Please become an IEEE member. I think 1/3 of you registered as non-members tonight. There are like many benefits in becoming a member. Please become an IEEE member, and also society members for the society. We had a joint event, Artificial Intelligence Symposium last year in November at Intel with same sponsoring societies. Now the videos and the slides are available online. The keynote speakers' videos are publicly available online now. We have for hardware track, Professor Rabbi from UC Berkeley, and software, Dr. Alex Esmola from Amazon. So those videos are available online, and also the rest will become available, become public very soon. Please check out the website, ai.ieeesiliconvalley.org. Signal processing for SSCS, we have 2 events scheduled in April and May. May, Professor Hajimiri from Caltech and Dr. Larry Nagel for April. And signal processing also will have 2 upcoming events, April 11th and May 1st. And those also will be on AI hardware in April by Jeff Beer from Embedded Vision Alliance, and also Application of Machine Learning in May by Professor Jan Auerbach from Purdue University. So those are, and we'd like to thank Yole from Signal Processing and Talo for sponsoring us, and also Rajiv and other CSXCom for the announcements. Just a couple of logistics. We're doing recording and we make the videos available online, so we'd like to ask you, so the speaker basically, his talk has 3 parts, and after each part we'll have a Q&A session. Because of the crowd, you don't have running mic this time. You'll have 1 microphone on the chair here, and 1 microphone on the chair over there. So you can just line up for questions and ask your questions after each part of the talk, and obviously at the end. And we'd like to ask you to switch off or turn it to vibrate your cell phone. And with that, we're done with the announcement, so we get to tonight's speaker. Tonight's speaker, he doesn't need any introduction. We are honored to have Professor David Patterson from Google and UC Berkeley to have a talk on 50 years of computer architecture. And actually, he was the plenary speaker at ISSCC in San Francisco on a similar, almost same topic, and we are honored to have him tonight. Just for the sake of recording, I just do a short intro. It's my great pleasure to introduce Professor Patterson. He's Professor of Computer Science Emeritus at UC Berkeley, which he joined after graduating from UCLA in 1976. And he's also a distinguished engineer at Google, where he helps with accelerators for machine learning. Dave's research style is to identify critical questions for the IT industry and to gather interdisciplinary groups of faculty and graduate students to solve them. His best-known projects are reduced instruction set computers, RISC, redundant array of inexpensive disk RAID, and network of workstations now, each of which help to lead to billion-dollar industries. He has won numerous awards, a total of 35 awards, just to name a few: CMC Prize, IEEE 1 Newman Medal of Honor, IEEE Johnson Storage Award, Sigma Test of Time Award, and ACM IEEE Eckert Mackey Award, among many other awards. And also, for our local chapters, he was the Silicon Valley Engineering Hall of Fame inductee in 2005. He authored 7 books, especially 2 books with Professor Hennessy, past president of Stanford University, on computer architecture, and he was chair of computer science at UC Berkeley and president of ACM. We are honored to have Professor Patterson. Please join me in the coming speaker.
Okay, so it's fun to be here and see some old friends and old students in attendance. This has 3 parts, and I'll pause to give you a chance to ask questions this time. First, 50 years of computer architecture in 15 minutes to set the stage for 2 exciting things that are happening: domain-specific architectures like the Google's tensor processing unit, and then this new open instruction set architecture of RISC-V. So let's go back in time. In the early 60s, IBM had this problem. They had 4 independent lines of computers. And each had its own instruction set, each had its own software stack, even different I/O devices, and niches and business models. So IBM boldly decided that they would invent binary compatibility, invent the idea that computer architecture would be defined independent of the machine and software was on everywhere. And they bet the company on this IBM System 360 instruction set that would take over all 4 lines. Now, one of the biggest problems for computer design then and today is control. That's the hardest thing to do. So how are they going to get all these independent business units to agree on the same instruction set? And they decided that they were going to bet on microprogramming. This was invented by Maurice Wilkes, one of the pioneers of computing in one of the first computers, and he thought it'd be a lot easier to design control if you did it via a memory. And in the technology he was using in 1958, the logic was more expensive than ROM or RAM, and ROM was cheaper than RAM, and it was also faster, so let's specify control as a memory. So they decided they were going to bet the way that they were going to have a common instruction set across these lines, that they have different microprograms for different hardware sets, from 8-bit wide data all the way to 64-bit wide data. So here are 4 of the models that they invented or announced on the same day, so from 4 to 64 bits. And the microcode here, as it goes across, the narrowest one was 50 bits, 4,000 microinstructions 50 bits wide versus a little bit less than 3,000 instructions 87 bits wide. And basically, for microcode, kind of the more parallel the data path, the wider the micro instructions were, and it didn't take as many steps as it did to be able to execute them. So it was wider and not as deep as typically done. And then they had different speeds of memory and different speeds of clock rates. And in today's dollars, they were amazing, impressive. They would rent them to you for anywhere between $500,000 and $2 million in today's dollars. So IBM bet the company on the idea of binary compatibility, and they won that bet. So IBM bet it and it came out in 1954 and dominated mainframe computers. And there's a descendant of that still running today. So that's the mainframes. Then comes integrated circuit technology that wasn't part of the mainframe. Now RAMs are about the same speed as ROMs, but Moore's law is in full force, and so memory is going to get bigger, which allowed bigger, more complicated microprograms, which allowed bigger, more complicated instruction sets, which we call complex instruction set computers. And the shining example of that is the VAX computer, the VAX 11780. It had 5,000 lines of 96-bit microcode, but you can kind of see it was a lot more complicated than the 360, and it was, but a very successful product. Back here in Silicon Valley, Gordon Moore of Moore's fame was pals with Gordon Bell of Digital Equipment Corporation, who was the architect of the VAX. And so because they were pals, Gordon Moore understood that microprocessors were probably going to become more significant, and that the next instruction set that they did after the 8080 was probably going to last for the rest of the company. He had enough instincts on that from talking to Gordon Bell. So what he did was he decided to start a project in Portland, Oregon, to be the future of the company, to set the instruction set for the rest of the life of the company. So he hired all these PhDs in computer science, put them to Oregon, and they were supposed to invent the future. And it was by far the most ambitious one. It was called the IEEE 432. It was a 32-bit address space at the time when even the 8080 was wasn't even a 16-bit address space. It was capability-based. That means the security was built into the address space. They weren't limited. They wouldn't have small code size, so instructions could be any number of bits. You could have 3-bit instructions, 17-bit buttons. There's no restrictions on it. And it was really big microprograms to get all that complexity in it. They even wrote their own operating system in the esoteric language Ada. So they're trying to invent the future. The problem was with a bunch of PhDs and computer inventing the future is they were late. But when they finally came out, they weren't modest. This is a quote when it was announced in 1981. This is going to be, every decade something comes along that's revolutionary, and, it's going to be as big a difference as analog computers were in the past. But unfortunately for the people in Oregon, it was very complicated. The microprocessor didn't fit in one chip, and it was performance. So Gordon Moore, trying to invent the future, they told them, by the way, we're going to be late. So he started an emergency project. He gave a team at Intel 1 year, and what they had to do in that 1 year is invent a new instruction set and build a chip and bring it to market with their 16-bit successor they gave. So they spent 3 whole weeks the last time designing the instruction set. They had about 10 person weeks altogether, given their schedule. They basically kind of made extended the 8080 in ways, made it, and it was supposed to be assembly language compatible with that. And they fitted the address set through segmentation between 20 bits, and it was only 30,000 transistors, and they brought it to the market with no fanfare, unlike the 432. It just made it. So thanks to Gordon Moore's great luck, that IBM decided to get in the personal computer market, and it needed a microprocessor. So they picked, now the Motorola 68000 was kind of an elegant instruction set architecture, very similar to the IBM 360 instruction set, and that was the favorite going in. But when they wanted to ship the PC, the Motorola 68000 wasn't ready. It was late, and also Intel had made a version of the 8086 instruction set that had an 8-bit bus, which allowed them to build a cheaper PC. So IBM adopted it. They thought there'd be 250,000 units sold, instead it was 100 million sold. So 886 became an overnight success, and because of binary compatibility that IBM invented, it had an incredibly valuable franchise going forward. And so 886, this emergency replacement, had this incredibly bright future to this day. What happened in microcode machines? This is a picture of John Koch, who was one of the famous computer scientists, Turing Award winner. And he took a look, and his group at IBM, he took a look at these mainframe computers. He was building a simple pipeline processor called the 801. It wasn't a microprocessor, it was a big ECL computer. So he ported his experimental compiler to the big mainframes, and what they decided to do was not use the complicated instructions. They just used the plain old loads and stores and simple instructions. And it ran faster. So if you didn't use the complicated stuff, it sped programs up, like factors of 3. So that was an idea. And what about a DEC in Boston who did the VAX? Well, 2 of the engineers there carefully studied it, and they looked at all of that microcode I told you about, and they found that 20% of the instructions were responsible for 60% of the microcode, and they were only executed 0.2% of the time. So hardly used at all. And a lot of those were the complicated instructions. So now the transition to RISC, you can think of it as basically, instead of having the RAM with this microcoded interpreters for these complex instructions, let's take out the interpreter and we'll just compile into these simple instructions, and instead of it being the memory for the control, it will be an instruction cache. So that means that since it's a cache, as you change the program, we can reload that fast memory and we'll kind of tailor it to the machine. And not only that, because it was pretty simple, you didn't have a microcoded interpreter, it was much easier to pipeline so it could run faster. And it turned out, as we saw before, the complex instructions weren't used all that frequently anyway, so how much were you giving up? By making it not very many transistors, the RISC architectures were able to fit a whole 32-bit data path. The control was relatively simple. And by fitting on one chip, of course, it was much more efficient. The problem was at the time, and I was just talking to a colleague at the time, in the early 82, 83, there were terrific debates at conferences about RISC versus CISC. And one of the problems was we didn't have a scientific explanation for why RISC was better. We figured that out later. In fact, my colleague John Hennessy wrote the first paper about this. So the insight that helped explain why RISC could make sense is this formula. So the time per program, how many seconds it takes to run, they have these 3 factors. The number of instructions you execute per program, the average number of clock cycles per instruction, and then the time per clock cycle. So those 3 pieces. So what the explanation was is that, and this was a study by the people on that slide from DEC. They did a study to be able to see what happened. And for the system instructions, did execute fewer instructions, about half as many, but the average number of clock cycles was 6 times as many. So when you multiply those 2 things, RISC was about 3 times as good as the VAX architecture in this case. And once we had that scientific explanation, I see, with the microcoded interpreter, you have the clock cycles go up even though you execute more instructions, and people kind of got it. Then the question was, interesting technically, would it be successful in the marketplace? All right. So what happens next is the PC era is in full flight. For the next, probably from the 80s through the mid-90s, RISC have by far the fastest processors, and the microprocessors are the fastest. So Intel didn't take that line down. They cleverly came up with an idea to translate the x86 instructions into what are either called micro instructions, or at AMD they're called RISC instructions. So they took the hardware resources to take these kind of wild variable length, variable clock cycles thing, which are hard to pipeline, and translate them in hardware and things that are easy to pipeline. And then they adopted some of the ideas the RISC guys came up with. One of the other ideas was super scalar, fetching more than one instruction sometimes, so they could do that. They did a kind of super pipeline, very deep pipeline. They could do that. Multi-level caches, they could do that. And then on their own, they copied from the old IBM 360 an idea of out-of-order execution, and they put that into their design. So given Intel's technology, they were able to overcome some of the disadvantaged instruction set and had the best microprocessors, the fastest microprocessors starting, I think, in around the second half of the 90s. and it eventually dominated servers, and they got up to amazingly 350 million per year. So that's the PC era. What's the post-PC era? So the post-PC era is in the phones that we all carry with us. So let's say it started with the iPhone in 2007. So it's no longer chips that you buy from an Intel or an AMD. It's systems on a chip. So Apple's creating a system on a chip, and they want to get IT to decide processors on chips instead of buying things. So that's a big change. And clearly, when it's on an SoC and you're integrating it yourself, you care a lot about die area fit in the SoC, and because it's mobile, energy is as big a deal as performance. So that's a change from before. And so that overhead of translating from the x86 instruction set into the internal instruction set was too expensive, too much to be adopted, and also there was no binary compatibility, had no value, right? You weren't downloading things to the PC and running it on your phone. So those two strikes against the x86, and they just don't appear, right? There's no phones with x86s in them, almost no tablets that will do it. So PCs are dwindling in the post-PC era, not surprising. They're dropping at about 8% per year in sales. Mobile phones are up and to the right, and Internet things up and right. So amazingly, last year there were 20 billion 32-bit microprocessors, almost all RISC processors that were sold. Now, x86 still dominates the servers that are in the cloud, but the cloud's not that many machines, right? Like one person estimated that all the companies together have 10 million servers there, so it's not that many chips in the cloud. They're very expensive chips, there's just not very many of them. So today, 99% of the processors are RISC processors made today. I just thought like just the ARM processor, where R and ARM is for RISC, they ship 100 billion chips with RISC processors in it. So RISC won the second war. What happens next in computer architecture is an idea that's going to replace both of them. CISC, RISC, very long instruction word is a better idea than the other two. The idea is actually related to microcode. Josh Fisher, who came up with the idea of DLAW, he did his dissertation on microcode like NSE and I did. This wide instruction where you control the data path with lots of things to control, and they would, as it showed in this example, depending on what you were doing, it would take a variable amount of execution time. So it shows there on the left, it would take maybe 1 clock cycle for the integer instructions, or 3 for the local source. So it was the job of the software to put the right things into those slots, kind of like microcode, but you're going to do it by compiler. So that's a very long instruction word. And so the architecture didn't have to do very much. It didn't have to check for dependencies between them. And it didn't have to, there was no interlocks or stuff like that. The compiler is supposed to do this. The compiler is going to fill all this in for us and make the hardware life easy. So it had the compiler was doing everything. It had to schedule the integer instruction parallelism. It had to avoid deadlocks. And that was the bet. So what happens next is the 32-bit address space. Intel successfully went from the 20-bit of the 86 to a 32-bit address space, just kind of widened the registers with the 386. But it was time to do that again. Now the problem, what they could have done is just made the x86 64-bit wide registers and solved it that way. But had they done that, they would have brought along AMD, which had rights to the x86. So that was a business problem. And then, the x86, they spent 3 weeks architecting it, so it wasn't the world's best instruction set. Here's a chance for them to clean slate. So as I understand it, the head of Intel and HP were having golf, and they found out each of them was working on DLAW, so they decided to join forces. So now you had Intel, the best chip manufacturer in the world, and HP, a formidable computer company, agreeing to do the same instruction set. They didn't call it DLAW, they called it instead EPIC, for explicitly parallel instruction computing, which is kind of a binary compatible version of DLAW. And they started working on it in 1994. It was announced that it was the successor, and AMD wasn't invited, so AMD was forced to just extend x86 to 64 bits. At the time, there was tremendous fanfare about it, saying that DLAW was the future, RISC and CISC was the past. And several companies, just once it was announced that HP and Intel are going to build the next computer architecture, They just gave up on what they were doing. SGI, others just abandoned and said, okay, you may not like it, but we have no choice. We have to use Itanium because that's got to be the future here. So their first chip was late, and it took a mulligan on the first chip, but the other chips came along. So then what happened to EPIC and computer architecture? It was an epic failure. There was three technical problems with DLIW. The first was very long instruction where you're trying to schedule it. First was unpredictable branches. That made it very hard to schedule. The second one was variable memory latency. So if you had a cache miss, it was very hard to software from schedule. And the last one was just the code size. It was called very long instruction words. The words were very long. The programs got bigger. So those three strikes got it. And as John Knuth, a Turing Award winner and one of the famous computer scientists of all time, said the Itanium approach was supposed to be terrific, but it turned out the wish-for compilers were basically impossible to write. So that didn't work. And that's what we do in computer architecture. How do we argue about RISC versus CISC or DLIW? What do? We spend billions of dollars on commercial products, put them in the marketplace, and see which one wins. So it's a very expensive field to have opinions on. So, all right. And so, given the tremendous fanfare around the Itanium and its doomed failure, that didn't go unnoticed. It became kind of ridiculed by the industry, and somebody changed the name from Itanium to Itanic. And so after an infamous ship, and this cartoon shows companies abandoning ship and trying to get away from the sinking Titanic. So kind of remarkably, what happened was the emergency replacement X86 survived yet another life, right? So the things that they had 3 weeks, 10 weeks to work on evolved the unit from 16 bits to 32 bits, and now from 32 bits to 64 bits, and it's still with us today, despite 2 attempts by lots of smart people to find better instruction sets. It survives. It's like Dracula or something. You can't kill x86 instruction set, despite serious efforts. Okay, so this will be time for part 1 of my comments. So what's the consensus instruction set today? It's not CISC. We haven't had a microcoded interpreter instruction set proposed since, in 30 years. And it's not DLIW. DLIW, because of the 3 problems I talked about, didn't get on in general purpose computing. However, for digital signal processing, it found a home. Digital signal processing doesn't have, the branches are easy to predict. It doesn't have caches. It doesn't have variable latency. There's software controlled memory. And the programs aren't that big, so the code size explosion is okay. So the DLIW did find a home in DSPs, but not in the general purpose marketplace. So the winner is RISC. Who would have guessed 35 years ago, with all the changes in technology, that the conventional wisdom on the best instruction set in 2018 is RISC architecture? Okay, so to keep everybody awake, I'll pause and see if we've got questions or comments. There's a question in the back. They'd like you to use the microphone, or I will repeat them if you don't want to do that. The question is, all right. Why don't you hand it back and I'll put, and there's a claim that Transmeta was a successful DLIW. Dave Dissel's one of my students. I don't think most people would list Transmeta as a success. I think it was an interesting thing to try, but I'm not sure how successful they were able to do binary compatibility.
There was a brief period when AMD's server chips were actually faster than Intel's, and my experience now is that AMD has fallen way behind Intel in server chip speed. Can you just comment on why that has happened?
So that's harder. Why did AMD? Well, first of all, I think part of the reason they got ahead is they had the 64-bit address and stuff done earlier than Intel did, and Intel had to catch up. Hennessy, fortunately for me, John Hennessy, despite having this little job as president of a major university, continued to help write the textbooks, and we just had the 6th edition of our textbook come out last December. And in there, I went through the spec benchmarks to see the latest AMD and Intel ones. And at that time, that when we published it, the difference was, if you use the spec integer benchmarks, about a factor of 2. And actually, one of the benchmarks, because Intel technology was, ran 2,000 times faster than everything, so you should throw that one out. But it's about a factor of 1.5. So Intel has very good, maybe the world's best semiconductor technology, and I would say using those benchmarks about 1.5 times faster. Intel's got really good people and really good technology, and they're especially it's very good at that. But despite their best efforts for at least 5 years of trying to get into low power embedded things, that was a difficult thing to do. Another thing that I heard kind of in terms of ARM there's about 10 places that make ARM things. Right? For Intel, it can only hit a couple of points. It can't do 10 points at once. It's hard to have many designs, so it's hard for them to get into the mobile market. They've been unsuccessful in the mobile market. Okay, why don't I do one more and then I'll get back. Okay. Okay, let me see. The two questions, one of them had to do with compilers getting better for Itanium, and the first one is superscalar and VLIW. Kind of the fundamental difference between superscalar and VLIW is superscalar does not rely on the compiler to work, right? Superscalar is binary compatibility. So old binaries run on a superscalar architecture. For the pure version of the VLIW, when you make it wider, you would recompile. You had to recompile. That's the pure version of the VLIW. Itanium can't do that. If Itanium compilers are actually work now, 10 years later, they're kind of 10 years, whatever it is, 10 years too late. I think Intel formally ended of life the Itanium just a few months ago. But it missed its window. Well, the superscalar, but it had the superscalar compilers. Compilers are aware of the microarchitecture to get performance, but they don't have to work. It'll run properly even if they're not perfect, right? But I think the VLIW bet is you better get pretty good performance out of the block, otherwise you're going to have poor performance when you're announced. And I think that's what, for them, even if they're right, maybe if Fisher is right, and 10 years after the Itanium, the compilers finally work, the marketplace is moved on. Okay, all right. That was a little commercial break. Part 2, domain-specific architectures. So, things are changing, right? The end of Dennard scaling, I'm sure many people have talked about the ending of Moore's Law. And from the computer architecture side, we had all these ideas that under the hood we run faster, and the programmer didn't have to worry about it. But that ended with it running out of power, and we had to switch from a single efficient core to lots of efficient cores. But Amdahl's law, the limited, there's only so much parallelism you're going to be able to take advantage of before you run out of core, so that kind of kicked in. And then we changed the proxies and servers. So what's happened, this is the first figure from Hennessy's in my textbook that we've been doing over whatever it is, more than 25 years. And in the good old days, before the CISC things, it was remarkable improvement. It was doubling every year and a half, 50% per year. When Dennard scaling stopped and we started running out of power, it slowed down to doubling every 3.5 years. And then Amdahl's law started, but we went to multi-core, right? Efficient cores. Amdahl's law started limiting the number of cores, so we slowed down to every doubling years. And when we just updated the textbook this time, I was shocked to see, using the spec-int benchmark, that over the last couple of years, it's only been 3% a year. 3% a year, which is like doubling every 20 years. So we have hit the wall in terms of single-threaded performance on microprocessors. So, transistors aren't getting much better, ending of Moore's Law. The power budget isn't getting any bigger, electron migration and things. We've already done the switch. What's left? And as far as I know in talking to all computer architects, the only thing left is domain-specific architectures. That is, you're not going to try and do everything. You're going to try and do a few things really great and not worry about the other stuff. Let the host CPU handle it. So now the question is, what are we going to accelerate? What are you going to pick to work on? Well, at Google, and about 5 years ago, they saw this excitement about deep learning, or deep machine learning as it's called, or neural networks. They thought that if everybody, all their customers, would just use Google Translate 3 minutes a day, and they calculate how many CPUs they would need to serve that, they would have to double their data center. So they had an emergency project to start that in 15 months, kind of like Intel did with 86, in 15 months, we need you to build neural network hardware that can handle this workload so we don't have to double our data centers, which we couldn't afford. So how fast is machine learning improving? So this is a slide that Jeff Dean put together, and it plots on the archive, which is a place that papers are published immediately, the number of basically machine learning papers relative to 2009, and the red line is Moore's Law. So the number of papers per day is going up by Moore's Law. So in 2017, if you were trying to keep up with what's going on in machine learning, you'd need to read 50 papers a day. And God help us next year, right? So this is an exceptionally exciting field of many things going on, and we've all heard the story about a machine neural network-based software program beating the human champion at Go in the last year. That everybody mentions that example, but it's also doing object recognition better. This is some of the technology that's having self-driving cars, so it's a very exciting field. So that's the one that worked at. And we need a lot more computational power. It's changing, it's popular enough, it's changing how we're designing computers. So what are some of the features? It's not a lot about precision. For machine learning, if you're trying to imitate a neural network, reduced precision is fine. And then the operations are matrix multiply. So if you got your wish list, if the architects get their wish at Christmas, what problem do you want me to solve in hardware? You would have picked matrix multiply, right? If it had been alpha beta search or pointer chasing, oh God, how do we do that? Oh God, oh God. Matrix multiply, we know how to do matrix multiply. So it's low precision matrix multiply is a lot of what's going on. Now there's two pieces to neural networking that are pretty easy. There's the learning part or training, and that's being done when you're developing it. So you're looking at data, it's learning from data, right? That's the training piece of it. That's what researchers do. And then once you've got something trained and it's going to go into production or it does prediction, that's called inference. So Google wanted to do inference because that was easier and because that was what they worried about, doing the translations for all the customers. Now the other thing about it, because the precision isn't that emphasis, although you would naturally think of doing it in floating point, you can also do inference in integer, and that's called quantization. So, and in fact, what Google did is decided to use quantization, so they did things in integer for inference. All right, and what they built, it's called the TPU. At the heart of the TPU is that matrix multiply unit. Amazingly enough, it's 65,000 multiply accumulant units. It's 256 by 256 matrix. If you multiply its modest 700 megahertz clock rate by that, you get 90 tera operations per second. So how many max is that? It's like 25 to 100 times as many as in CPUs or GPUs. Now, the results come out in basically vectors into the accumulator, and that's 4 megabytes of accumulators there, and there's also a kind of a scratchpad storage, and that's 24 megabytes of scratchpad storage, which is like 3 times as much as the GPU. Now, you couldn't fit everything on the chip, so the weights that are associated with neural networking or parameters are kept in DRAMs off the chip at the top through a DDR3 interface. Because they were in a hurry, they had to get it done in 15 months, they couldn't use more aggressive memory technologies than that. So that's a pretty standard technology, much slower than what GPUs use. Okay, so that's logically, here's the floor plan. There's the floor plan. The matrix, okay, one more. Okay, the matrix multiplier unit is a quarter of the chip. That's the 65,000 max on it. The memory is about a third of the chip, so 2/3 of the chip are just the memory and the multiply unit. Control is only 2% because they have a very simple control that's being done with it. So that's kind of the floor plan. In computer architecture, we grade on the curve, right? So what are you going to compare it to? So the chips of the time that we went into Google Data Center in 2015 when the TPU started working were the Haswell generation, which had 18-core CPU, and the NVIDIA Kepler one. Those are, at least in that time, those were really big chips at about 600 millimeters squared. The TPU is about half of that, and also they use a lot more power. They use a lot more power, about 150 watts, and the TPU is half that as well. So that's what we're going to compare to. Now, to try and present the comparisons, when you just talk about peak performance can be misleading. So in my past, one of my PhD students came up with this visual model trying to explain performance that lists memory bandwidth, memory capacity, or memory bandwidth capacity and computation capacity, and he calls it the roof line. So this is the graph over here. So what the y-axis is on log scale is floating point operations per second. And so the peak performance for the TPU, that's 90 terops, you can't go any faster than that. That's the speed of light. Now, what the x-axis here is the bottom is arithmetic intensity, and that's the average number of operations you get for every byte you fetch. So it has a lot of operations. It's over here on the right, and it has fewer operations from the left. So what this slope line is, it turns out when you plot it this way, that's the memory bandwidth. So what's the bandwidth of your memory forms this slope part, and that's why we call it the roof line, because of those two pieces. So then if you have a lot of operations per byte fetched, you're over on the flat part, so you're computation limited. If it's few operations per byte fetched, you're memory limited. And so that's the idea, is to show visually. And so the question is, for your applications, you hear a number like 90 terops per second over here. Well, that's interesting, but you want to know the question is, how many arithmetic operations per second is your application? Because it doesn't matter what that is. Let's look here over here. Okay, now let's go look at it. So the TPU has a really steep roof because it doesn't have very good memory bandwidth. We use those DDR3 memories to get to it, and so that was relatively slow compared to its incredibly high operation rate. The good news is that the applications, if we look at the arithmetic density and what performance delivered, are very close to the roof line. So the idea of the roof line is that you can't go faster than that. So if you're near it, you're happy. That's the limit of what the computer can do. So 5 and 6 of them are pretty close there. Let's look at our competitors. The CPU Haswell, it's more balanced design. It's got the memory bandwidth versus peak, and you can see that's where those same 6 benchmarks are. The GPU has a higher roof line of there, and it's got even much better memory bandwidth, so it's got a more attractive shape because it's a lot easier to get peak performance if you're to the right of this ridge point here. However, you may have noticed there was a big gap between them. They weren't bumping their heads against the roof line. They were below it. The reason had to do with response time, which was a surprise to us. So if you think about inference, it's dealing with user-facing applications. So what the people who run those applications care about isn't how fast the throughput of your computer. They care about how fast it is under the worst case response time, 99% response time. So for the GPU and TPU, it shows the difference between if you didn't care about response time, how much faster would it be, versus you had to hit the 7 milliseconds deadline for this application. And it's about a factor of 2.5 there. So for the TPU, which is a very simple design, has one matrix unit, and is single-threaded, the gap is much smaller. So fortunately, because even though we didn't know it at the time, or the architects didn't know it at the time that they did the CPU, is its response time is going to be rigid. It's a pretty simple design, so it's not much variability, so it was very close, unlike kind of traditionally what you do in computer architecture is you worry about the average case. But for inference, worst case latency matters. Okay, so that's what it looks like when you put all the roof lines together, and all of the ones for the TPU, all the stars for the TPU are higher than all the roof lines of the others. Now that's on a log-log scale, and I don't think log-log, so let's put it on a linear scale to see what they look like. And so, yep, it's a lot faster. Okay. So on average, it's the GPU is about twice as fast as the CPU in that case. The TPU is about 30 times faster, so the TPU is about 15 times faster than the GPU. Now, from a data center perspective, performance is interesting, but what you'd really like to know about is performance per TCO dollar. But there's no way companies are going to release the TCO information. The good news is TCO is related to power, and we can release the power. So this shows the performance per watt measured two ways in the relative performance. On the left is, these are accelerators, so there's a host you plug them into. So this includes the power for the host on the left, and on the right, we just talk about the incremental. We ignore the host part and just talk about that. So if you look at these numbers here, it's a factor of 80 times the performance per watt of the CPU and about 30 times of the GPU. Now you remember I talked about how the slow memory bandwidth, because of the rush there, and you saw on that roof line a lot of the things were under the slow part of the roof, which was memory bandwidth limited. So the natural question is, what would happen if we use faster memory? What would happen if we use the same GDDR5 memory that the GPU was? So if we put the 2015 GPU style memory unit, what would happen into performance per watt? And it jumps up even higher. A revised version with the same memory as GPU would be about 200 times performance per watt of the CPU and about 70 times that of the GPU. So here's a picture of the board, and here is a picture of I can't remember, 64 of them together, and this is actually the one that was used to beat the Korean champion of Go. That the AlphaGo ran on this hardware. It's still it's being used. Billions of people use this thing regularly. It's used for search and machine translation and so forth. Okay, a retrospective here, and this is a slide that I got from Cliff Young just for you. It wasn't at ISSCC. So, because of the compressed schedule, they put everything in software that they could, and has some features of insurance policy that worked out pretty well. The ASIC flow made the machine much lower power than they expected. They were thinking it would be closer to 170 watts, but they came in at 75, which is helpful. The architects thought they were building a throughput machine, but it turned out to have a low latency requirement. To their surprise, they talked to the application people. They didn't push response time the year before, but when it was time to port it, then they really cared about it. Why should you study computer architecture? Why should you buy computer architecture textbooks? So three ideas from the 1980s, before many of you were born, were vital for the TPU. The first is that matrix multiply unit followed the idea called systolic arrays. This is an idea from 1980 where you can get, if you kind of orchestrate where the data flows through the array and they meet up, you can do this without register accesses, which saves both power and area. So one of the big ideas was systolic arrays in 1980. When we were fetching from the DRAM off the chip, there was an idea called decoupled access execute, is that you don't wait, you start the memory transfer and you don't stop the instructions, you keep going and let the data catch up. That's called decoupled access execute. That's from 1982 by Jim Smith. And then because we were shipping the instructions to the GPU over an I/O bus, it didn't make sense to ship RISC instructions, one clock cycle. We had these things that would take many clock cycles, so we used CISC instructions right from the 1980s. So if you're young and don't learn history, you're going to suffer. You need to buy textbooks, I guess. So the quantization turned out to be harder than we expected. The early users were very sophisticated and were happy to do that, going from floating point and making it work in integers. Not everybody wanted to do that. And matrix multiply turned out to be a great primitive. You can do lots of things with that. You can do memcopy if you put identity matrices in it. You can concatenate things together. You can stride, you can average. So it was a pretty powerful tool to be used. And then it was very, programming a single thread of control, unlike what the CPUs and GPUs did, which have lots of threads, made it a lot easier to do, and it also gave us that value of response time. Now, the TPU B1, the one was, for instance, what about training? Training is what all the researchers spend their time on. It takes, I don't know, it takes days or weeks to train something. When we're doing inference, it can take milliseconds. Can we do hardware for that? And that was version 2 of the hardware that Google announced about last May. This is does both training and inference, does both, not just one. So here is a version of the design. It has, this is the so-called high bandwidth memory. So this is the same memory that you'll see in GPUs. This, it's a technology stacking thing with interposers and stuff like that. There's 2 what they call tensor cores and a scalar unit in there. The memory bandwidth is between these is 600 gigabytes per second, sorry. So it's floating point because training is a floating point, and it's 128 by 128, where the prior one, the TPU, was 256 by 256, but there's 2 of them in there. It's reduced precision, and it does 45 teraflops. Here's a picture, and they could put 4 of them on a board, so the 4 boards, 4 times 45 is 180 teraflops, 64 gigabytes of HBM memory, and more than 2 terabytes per second of memory bandwidth. Now, that's a board, but this one, unlike the GPU, is designed to be connected together to build a much bigger computer, and that's what this one is. For some reason, it's called the pod, is the word they describe it, but it's 64 of those TPU cards. You can see the ribbon cables connecting them all together. That's collectively 11 petaflops for machine learning and 4 terabytes of HBM memory. This shows the scalability on one of the popular image things called ResNet, and so it's very close to linear scalability, which is great. And it's programmed in TensorFlow, which is this open source thing that Google is running. It's kind of a domain-specific language for domain-specific architecture. And recently it was announced it's available in the cloud. So the first generation CPU is just used internally. The second generation CPU for inferencing is going to be in the cloud for rent. So, and they quoted a couple of early customers that were very happy using the version 2 GPUs. So wrapping up this before time for questions, the domain-specific architectures are a thing. General purpose CPUs are not getting a lot faster. That's the only thing we have to do. Deep neural networks are a popular area because they do lots of tasks. If you make it do neural networks, they get used for translation and search and ads and games, all kinds of things. The first one is for inference. The second one is for training and inference. And if you go online, you can start seeing people showing comparisons using the cloud platforms of GPUs and GPUs on the cloud, because anybody can use these things. Okay, so I'm ready to wake you up again for the next set of questions around domain accelerators and GPUs and stuff like that.
Hi. In your pod picture with the ribbon cables, what's the signaling and speed on those?
Oh, sure. Yeah, I'll tell you that for sure. Now that I've retired from a professorship and work for a company, I have learned that you don't reveal product information as part of a talk. So what we did for the first TPU, we wrote a very detailed paper that was published later after the announcement, and we haven't written that one yet. So I can tell you exactly what's on the slides, and I cannot tell you anything that's not on those slides. But we will write a paper that has all the details.
Hello? Yes. So
where?
Here. Here.
Okay.
Yeah. As a professor, former professor, and as a Google employee, how do you feel about the privacy implications and ethical implications of parts of the talk, like the business model of
privacy or
privacy, surveillance capitalism, as they call it, that putting effort into that kind of technology that is ultimately used to spy on people, essentially?
I didn't follow that one.
Yeah, how do you feel about using, as an academic, not only as a Google employee, of putting your brain power in enabling...
How do I feel about putting my brain power to build hardware accelerators?
No, hardware that makes spying on people easier.
What is it?
Spying.
Spy machines. Oh. I guess I don't... why is that a spy machine? I don't...
Let's just limit the questions to talk about...
I'm pretty sure I'm pretty sure if you worry about spying, you should not be in the computer industry. I think everything is useful for spying. I don't think this is any more useful for spying than anything else.
So I have a question on computer security. So since you are sharing these TPUs in cloud that can be rented by GCP cloud people, if their workloads are there, how do you keep them secure from?
Yeah, so for the, well, you know the answer to this. So basically, Amazon, in 2006 pioneered the idea of using virtual machines, and we bet on virtual machines to protect customers from each other. And I think Amazon's been, when Amazon came out with that, there was a lot of skepticism that people would ever use it, because especially for sensitive data. And it's possible that that's flipped now, where given all the break-ins you read about people who own data centers in the headlines in the newspaper every day, there's a question whether your system administrators for your internal data center are better than Amazon or Google's system administrators in doing that. So it appears that virtual machines in the cloud is arguably a more secure platform than, people buying computers themselves and running them themselves. But virtual machines are the key technology. And so there has to be a mechanism to use accelerators that honors the isolation. A few more questions?
Yeah.
Over here. Okay.
So when they ran the program that defeated the world champion in Go, they found that as the program was learning how to play Go, after a while, it was doing things and executing strategies that nobody could understand. Likewise, in financial technology, now they can analyze a huge data set, and they can say, you should buy this, and it works. And the customers say, well, that's great, but what is the methodology your computer developed? And the answer is, I don't know.
Yeah. So you're asking me questions about machine learning, which is not what I write textbooks about. But I could say for the Go one, what I find really interesting is I don't know that I would say they didn't know why. I would have said it differently. I would have said human beings for this complicated game had turned out to have explored a pretty narrow space. And apparently, if you want to be a Go master, you kind of memorize all games ever played. And originally, the first version of AlphaGo would learn those games and then explore on its own. But then they did AlphaGo 0, the next generation, and it didn't get a starting point. It was just, here's the rules of Go. Learn to play. And it's much more fierce. So you could argue that humans have, one argument about machine learning is humans have a limited number of things that they can understand, like this magical number 7 plus or minus 2. There's so much that we can keep for hand, and so we can explore a limited, in a big space, we can only do, there's a limit things we can do. Machines don't have that problem, right? If it's 1,000 dimensions, they can do that. So the machine learning argument could be, it's just, there's more situations where humans are limited to what they can explore, and we can do this machine learning. The area of I happened to go to the last December to one of the main machine learning conferences called NIST, and what you're referring to is explainability, and that is an active area in machine learning. So of those 50 papers a day, there are people who are trying to work on how are we going to make it explainable, and it seems like for things like loan applications and stuff like that, just saying no or for health applications, saying no or you should have surgery won't be sufficient. We'll need an explanation. But that isn't one of the active areas that are going on. Okay, I have time to I'll do one more, and then I'll do the rest of my talk, and then we'll have questions. So, okay. I recognize that guy.
Hey, Dave. By the way, Jeff Dean is your academic descendant. You didn't mention it. You're too long.
I didn't know that.
Yeah, he's my great-grandson. I'm your son, so there you go.
I didn't know that.
So computer architecture, I tried to think of the best question I could for you, okay? So we had cost, we had speed, we had physical size, then power came along, and that was a big change. What's the next big surprising change that's going to come along that we're going to have to worry about as computer architects?
I think I'm going to talk about that. Good thing. I'm going to start talking about open RISC-V, and then I'll do questions until you get tired. But I'm going to tell you what I think the next one is. A good meeting. Okay, so if we look at one of these SoCs that I talk about, there's a lot of instruction sets on it. There's the ARM one that everybody knows about, but there's all these others, graphics, DSPs, power management, with their own instruction sets, their own software stacks. And one person told us that typically there's a dozen of them. So do we need all these different instruction sets? And do they have to be all proprietary? What if there was one that was free and everyone could use for everything? What would that world be like? So RISC-V is what started at Berkeley. It's called RISC-V because there were, in the 1980s, we had four generations of RISC chips. There was RISC-1 and RISC-2, and Dave Unger here was PhD. He worked on what we called small talk on a RISC restore, and there was a generation after that called symbolic processing using RISC, which is FIR. So that's kind of the four generations. So I told the students in the faculty there at the time, I don't really like going back in history, but if I had to do it over again, I wish I'd been like the Illinois guys. They called it ILIAC 1, 2, 3, 4. And it should have been RISC 1, 2, 3, 4. So I told them that story. So when it became time to do another instruction set, they decided we were going to do a RISC instruction set on our own, and they named it RISC-V. And they used V for Roman numeral 0 because the RISC ones were Roman numerals. Well, why did we invent our own? Why did we use x86 ARM? They're just too damn complicated, and we would have got sued. Intel was one of our sponsors, but even they didn't want us to use x86 because they didn't like the idea of an open RISC out there. So we did a 3-month project that was led by my colleague Chris Kazanovich and two graduate students at the time, Andrew Warner and Wilfred Lee. Let's do it brand new, clean slate, learn from the past. And it took more than 3 months, but we were building chips and stuff like that. But a weird thing happened. If you teach at universities like Dave Unger and some of us have done, you get complaints from industry all the time about what you're doing, right? But this is a new complaint we never got before. We were using our classes in our instruction set in the spring. We changed it over the summer to make it better for the classes, and we got complaints from industry about changing our instruction set. Why are you complaining about what we changed for our internal courses? Well, the courses are on the web. There were people out there that wanted to have an open instruction set, and they looked around. They were trying to find one that they could build that wouldn't have proprietary restrictions, and they found ours and they liked it. So once we understood that, we thought, well, that would be a great idea. Let's try to make that happen. And so that's how RISC-V became an open architecture. That's this question I want to ask. I just want to see, how many of you before today had heard of RISC-V? Let's see. That's good. Good. I'm going to answer. Okay, so what's different about RISC-V? It's really simple. The x86 is 2,500 pages. You know, if you were to spend 8 hours a day, 5 days a week for an incredibly boring job of reading that manual, it would take you a month to make one pass, right? And RISC-V, you could do less than a day. It's a clean slate design. It takes the good ideas of that, avoids the mistakes. It doesn't tie in microarchitecture stuff like delayed branches and stuff like that. It's a modular instruction set, which is kind of a new idea. There's always been, well, you could leave out the floating point, but this is a real modular instruction set. The very base is incredibly simple. In fact, it's really close to RISC-1 instruction set. They're almost exactly the same. And then if you want some other features like atomic instructions or floating points, or even multiply divide, you add them, but you leave them out. Why did we do that? So that it could be good for Internet of Things. A little tiny, where every nanometer matters. It's designed for extensibility specialization. We understood that we were entering this era of the post-Moore's Law era of the accelerators, so we wanted to make it easy to integrate if you wanted to bring it closer together. And it's stable. The pieces have been done, they're frozen, and the other kind of thing that you didn't want to do is leave it up to some company. Companies come and go, and instruction sets come and go with them. We've seen instruction sets move and things like that. And you didn't want to depend on a university to do this. So we started a foundation imitating like the Linux group. They have a Linux Foundation or the LLVM Foundation. So we started a foundation and handing it over to them. In details, there's actually a couple different instruction sets, 32-bit and 64-bit. The extensions that are optional are the multiply divide, the atomics, single and double precision, and they have a nice vector instruction set architecture rather than the kind of clunky SIMD architectures that you see. And a nice simple RISC encoding to make it easy to build, and it's been frozen for a while. The foundation is catching on, and we do workshops twice a year. The last workshop was last November. It was at Western Digital. The next one's going to be in May in Barcelona. There's more than 100 members of the RISC Foundation. There's more every week. What's really interesting is about how we're going to evolve the instruction set architecture. Is classically, if you work for a company like AMD or ARM, you kind of talk, when you're going to change the instruction set architecture, you try to talk to some customers, you carefully think about it, your engineers announce it, and then you release it on the world, and then all the software people complain about it and tell you how you screwed up and stuff like that. So because it's an open architecture, we don't have to do it that way. It's more like a standards committee. So we have a group that's interested in bit manipulation instructions, a group that's, what does it mean to be RISC-V, they're going to work on that, a debug standard, what are we going to do about the memory model, the privilege spec, let's work on that, the new vector instructions, things on security, and so on. And we have that discussion with everybody in the world, all the world experts, giving input in the beginning, and then we reach a consensus, and we adopt it as a standard, and that's the way we're doing it. So that's an interesting opportunity for open source to bring all these people in, because not all, one company doesn't have all the smart people in the world. This way we can rope lots of people into it. So what do I think? So I think clearly the domain-specific architectures is the big thing, but that's not the next big thing. It's the thing. I've been bothered my whole career about how bad, it's embarrassing how insecure computers are. It's just, we're enabling purple-haired people in Eastern Europe to be criminals that can steal money from well-meaning Americans and get away with it and never catch them. We're enabling all that because we didn't worry enough about security. I think architecture is to blame for it. What did we do for security? Let's see. 1960s, we did page-level protection, okay, and virtual machines, and that's from the 1970s. Not so much for the last 30 years. So what has happened, if you look at when IBM came up with binary compatibility, that's basically their definition. What does it mean? It's what does the machine language programmer need to know to write a correct program, but timing independent. You don't know how fast it's going to be. Well, what Spectre has shown is that speculative execution allows you to see a conflict, performance conflicts, and they can do timing attacks and reveal secret information. So because we said architecture is defined as you don't worry about timing, but timing is something we have to worry about if we want to keep secrets. So this is an existential threat to computer architecture. As Mark Hill says, one of my students in this thing, we need computer architecture 2.0 that defends it. So this is a big deal. So the things that people may be poke fun at ARM and x86, they weren't bugs in their architectures. They're bugs in the definition of computer architecture, and they were just doing what was done before. So what we need to do is, how are we going to fix this? So I think RISC-V could play an important role. So FPGAs are amazing in their plasticity. You can change them, and they run pretty fast. RISC-V has, because it's an open architecture, that enables open source implementation. So there are several implications of RISC-V that you can just grab and download and start using, plug it into your FPGA. You get a full Unix operating system, full software stack, so you have a real system that's pliable that you can play with. Now, it runs at maybe 100 megahertz, but if you're connecting that to an internet and providing some kind of service, maybe you don't have as many users, but it's a real thing. It's a real computer. So this is going to be a great platform for trying out security experiments. And security, my colleagues in security, in the past have often been just critics. It's like, oh, look at Microsoft, you have a bug in your interface, ha ha ha, right? So but they're not putting something out there to get criticized themselves. This means they can do that. They can do a design, put it out there. And not only does that make it easy for people to do this in one company, because RISC-V is open, everybody can work on it. So we can get smart people at universities or any organizations to work on this really critical problem of to improve the security. So I think RISC-V is a vehicle that could accelerate. If we wait for the proprietary instruction set for them to make changes, it's like every 2 or 3 years. We could make changes daily. We could have lots of people working on this. So I think, it's not only a great opportunity, it's kind of kind of as moral people, our responsibility in architecture to make security a lot better, to do our part, which I don't think we've done. And we want everybody working on it. Okay. If you'd like to do that, Andrew, if you'd like to learn more about RISC-V, Andrew Waterman and I wrote a very slim book, very cheap slim book, like some other books on RISC-V. And so let me wrap this up with questions. So yeah, to me, given everything that's happened in the last 25 years, I did not expect RISC still to be a good idea. This idea, like our colleagues in operating systems and compilers and databases, that we could have open source ones that complement the proprietary ones, is exciting to see if it works. Since it's worked in software, I don't see why it can't work in hardware. RISC-V itself is a lot simpler, which helps with verification and can help with security as well because it's less attack areas. It's extensible. And it's got this competition thing. There's a small number of places you can work and make x86s or ARM, but everybody can work on this, which I think means more competition and better innovation. And our modest goal for RISC-V is world domination. It's the same instruction set and everything from your Internet of Things to your mainframe computers. Okay, with that, I think I said all these things. Oops. Yes, and this is exciting times. I think we're going to see this new renaissance between RISC-V and domain-specific architectures. Venture capitalists are investing in hardware startups. What a remarkable thing to say. It seemed like, you had to be in software to get new venture startups, but according to New York Times, he was able to count at least 45 hardware startups and, hardware for machine learning that's being gone on today. Okay, with that, I'm ready for questions.
Let's start here.
Hi. Thank you. Thank you very much. I'm going to apologize in advance for asking an architecture person this, but 80% of a microprocessor's life is really the ecosystem around it. And so I'd like for you to comment on the growing ecosystem around RISC-V because it's tiny right now.
Yeah. So what about the ecosystem around it? So, but this basically this is like crossing the chasm, right? Any new technology is going to have weaknesses compared to the existing technology. And so I think if open source software had not been successful, it would be hard to be optimistic. Kind of the question is the community around RISC-V going to fill in the missing gaps on the ecosystem around it? I can, like we didn't have a debug spec. Now we have a debug spec. Why did that happen? Because the people in the community said, you don't have a debug spec, you've got to have a debug spec. So there's pieces that are missing. We've got a really good a GCC compiler, but the LLVM compiler is behind. So there's software pieces and bus standards and stuff like that. And, the interesting test for our field will be rally around the open source, or the open architecture thing, as our colleagues in operating systems and databases did. And, what made Linux happen, I think, was not only kind of the academics working in it, but eventually companies like IBM and others decided this is going to be important for our technology, put engineers on this. So, is that going to happen? The things I forgot to mention, though, even in its nascent state, is NVIDIA announced that they're going to use it as a microcontroller in all GPUs, so that's tens of millions of chips per year. And a few months ago, Western Digital announced that they're going to put RISC-V cores in all of their disks. So that's going to be billions of chips per year. So those are so the early signs are good, but clearly the ecosystem isn't as good as something that Intel and AMD ARM have been working on for decades. But it's quite a bit cheaper. At the question of hardware vendors for Western, at the workshop, Western Digital announced that they were investing in a RISC-V startup company called Esperanto, that they did for
Okay, two small questions. First one from the history. Have you seen any application of the so-called wave pipelining in any of the modern architectures?
The question about wave pipelining, there's a startup company called Wave that's doing, I think, wave pipelining,
Okay, I'll send that out.
But by the way, all as far as I can tell, all ideas ever invented in computer architecture are being investigated right now by startup companies.
All right. The second.
You remember wafer scale computing, the thing that sank Almdahl? There's rumors that there's a startup that's even doing wafer scale itself.
The second question, since Amazon is not one of your employers, can you give some insight about whatever you know or can imagine about what Amazon is doing with architecture?
No, I think I'm pretty sure I could get in trouble for that too. I think I saw some speculation that in a publication that they were doing hardware too. I can't remember where I saw that, but there was some online place. I think they hired a guy who did a lot of FPGA. So Microsoft is, rather than doing chips, Microsoft has this project called the Catapult Project, where they're putting FPGAs in every server, and you're programming the FPGA to tailor it, which is an interesting idea. And Amazon apparently hired a person who had done a lot of FPGAs, and so people are speculating what they're doing. But yeah, I don't know. I mean, your guess is as good as mine. Okay.
Hi, Dave. Last time we saw each other, we were assistant professors in Berkeley.
Okay.
So my question was back to the plot. When you have such a monster amount of computation, how do you carve it out between all the applications that want to use it? If you can
I would say, let's see. So what's great, deep learning, deep neural networks have many wonderful features, and one of them is for training, is these are giant jobs. So people can tie up hundreds of GPUs for days or weeks. So you don't have to have that kind of time slicing thing that you would need to have for a mainframe computer. So I'm not actually sure what the scheduling plan is, but there certainly are tasks that would use all of that for many days. In fact, what Google is figuring out right now is they put this stuff into the cloud. They right now going to customers and see what they think. What do you want? Right? They don't really know what's going to happen here, and but there certainly seems to be enthusiasm for these large things together for training, because you can train a lot instead of training taking weeks. Maybe with 64 things getting together, you could do it in an hour or something like that. But this is what I didn't say this. But this is a remarkably exciting time. This is why I think of it as a golden age in computer architecture. Is there's all this demand for new ideas at the instruction set level, and one of the things we'll see is will these pods be incredibly attractive to be able to train really fast and really market there, and we're going to learn that in the next couple of years. Okay.
Question about the precision. Previous, actually, you say the 8-bit may be enough for the influence, but for the training, maybe 8-bit is not enough. Can you actually elaborate that?
Yeah. So one of the questions, the question is, what's the precision you need for training? It's a thing I've been wondering about. There are papers that will claim you can get away with. Sometimes training can be done with less bits. It certainly, NVIDIA latest chip has 16-bit floating point support in there, and there are things that run at 16-bit floating point. Colleagues at Stanford, like last week, announced a paper that where they think you can do training in the inner loop in 8-bit integers, and the outer loop you accumulate in floating point. So it's an active area right there, and there's not a final answer. The default thing to do, and the reason GPUs are so popular, is just do it in floating point. 32-bit floating point is enough. I think nobody wants to do more than you don't need 64 floating point. Everybody agrees on that. How much you need to do training is still an area of active investigation, and if we can make it a lot narrower, that would help our memory bandwidth and simplify the chip. So lots of researchers are looking at it, but I don't think there's a final answer yet. That's another reason. It's something that's fundamental. You think there'd be an answer to, but it just shows how new the field is. That's still open.
If someone was to make a web server chip using RISC-V, how much better do you think it could be than an x86 server chip?
Well, x86 is a tough. I mean, Intel's been building those for a long time, and they're very sophisticated. Branch prediction and out-of-order execution and things like that. 3-level caches, and there's a lot of architecture work in there. Now, if you that's going to be the hard one. if you're kind of lower into the lower end, like Internet of Things or mobile devices where you're not running a full Intel chip, that's probably a better opportunity for RISC-V because the benefits of the instruction set are more visible. Basically, the bigger the chip, the more aggressive the chip, the less the instruction set matters, and that's RISC-V's advantage for right now. Now, there are companies like this one I mentioned, Esperanto, that is trying to build a very aggressive design to, I think, to compete at the high end of Intel. And so we'll see how that does. But right now, I think the best chance is lower end, especially for the chips you can get right now. Where?
Hi, Prof. I wanted to know your input on newer radical architectures, which are more academic right now, like neuromorphic architecture. What's your take on that?
Yeah, so what's great, and Berkeley played a role in this, is for a long time, computer architecture has been driven by benchmarks. There was a time we didn't have good benchmarks, but for, 30 years we have had good benchmarks, and that's how we make decisions. Machine learning or vision things used to not have benchmarks. They just like, I've got a new vision algorithm, here's my picture, look at how good it is. Oh yeah, look at my picture. Look how, and so they were incomparable. But they have switched over and now do benchmarks, and they actually have competitions to do that. So the so-called neuromorphic, which means kind of brain-inspired things, and there's things like spiking neural networks that kind of imitate the brain. So far, those people who are advocates of that have not entered the competitions that everything plus does. And so there's, I think, skepticism until they start entering competitions and doing well. How serious are they? And why are they afraid to enter competitions, right? It's because they wouldn't do well. So the value of the competitions, it goes with this thing that's called ImageNet. In 2012, there was this guy at Toronto, Jeff Hinton, said, I think convolutional neural networks are going to be great for images. He called up a colleague at Berkeley, and why don't you believe me? He says, well, you don't enter a competition. So he called back a month later. If we entered this ImageNet competition and we won, would you believe me? Sure. So he got a PhD student to work on that, and he put it in, he found a GPU to work on it because it's floating point. And because the student didn't want to write, his advisor, Jeff Hinton, said, well, as long as you improve the accuracy 1% every month, you don't have to write your dissertation. So he worked hard. Of December, they submit, and they won. And they won, and they crushed it. They were much better. So the second year after that, that was 2012, 2013, somebody else won, and there was a handful of neural network entries. In 2014, it was 100% neural network, right? So the field, the competition changed the whole field, and people had kind of like saying about AlphaGo, they had all this code, all the right way to do it, and they threw all that code away and used much simpler algorithms, trained in a lot of data, and that was better. So that the field was forced to change as a result of competition. So if neuromorphic or spiking things are really better, then there's a vehicle how to convince people how to make that change, and so we have to wait for them to try. Okay, I'm not controlling the mic, but.
Hi, you mentioned domain-specific architecture and FPGAs. I was just wondering, because not every company has money like Google to make their own chips with a domain-specific design. So do you see FPGA in the future serves a compromise between the chips and the general purpose?
Yeah, part of the question is whether it has to be expensive to keep building chips. There's certainly work that's being done at Berkeley to try and make that a lot easier to do. I do know, I'm surprised, one of the benefits is, with where Moore's Law is today, is the tiny little test chips that you do that are a couple of millimeters on a sign, they have a lot of transistors, millions of transistors. So amazingly, you could go to TSMC, and for $30,000, you could get 100 chips, tiny chips, that have millions of transistors on them. So you can do prototypes that way, and there's languages that are much easier to design than Verilog to be able to do it. There's one at Berkeley called Jizzle. So we're trying, and there's people trying to work on bringing that cost down. So if it has high enough volumes like deep neural networks, a custom chip is probably justified, but there's a whole long tail of things that it doesn't make sense to build chip for. And for those, I think FPGAs are a pretty good use, right? But, you know, for neural networking, I think you can make a case that you should be building chips, which is why there's 45 companies trying to do it. So that's going to be that kind of investment, you know, frequency, popularity is going to, well, I think we'll see.
Hey, Dave, I'm sitting here remembering in the 80s when I was studying architecture with you, and we laughed at certain technologies, including data flow and artificial intelligence, which had this promise for all these years. And so turned out there are some things we were wrong about, and that happens. The world changes and you're wrong. But the question is, what are some of the things we all believe in this room that might turn out to be wrong tomorrow?
First of all, let me talk about AI. The difference, what's winning today, the people in the field make a big distinction between AI, writing logic rules, and machine learning. Those are two different groups. And some of them don't like being lumped into AI. So the machine learning group tends to be statistics, problem focused, solving a problem at a time, and it's working, right? So the AI in the past, followed by the AI winners, were leaders of the field promising things they couldn't deliver for. And that happened a few times. Says, wow, next year we'll be able to do this. Look at what we can do now from this simple example. Next year we'll do this. The difference now for machine learning is the excitement is around them doing things, like, you know, commercially viable for language translation or for object recognition. So I don't know that we were wrong about AI. I think the logic-based AI stuff didn't work. For data flow as a hardware technique, the classic MIT data flow thing hasn't caught on. The thing that did work is the out-of-order execution stuff. That actually goes back to the 1930s. So I don't know if they're wrong there. The thing that everybody believes that
it might. You don't have to be absolutely right on everything, but give me three if you can. It'd be great.
Three things that we all believe in that could be wrong. I don't know that I can. Next question. If I come up with it by the next question, I'll answer. Okay.
Yes. The one thing we didn't talk about is supercomputing. It was a hot topic also in the history of computer architecture. What do you think the future of supercomputing could be like?
Yes. So it's been, interesting. We talk about parallelism and stuff like that, and kind of somehow we characterize the problem of parallel execution of a single program is the thing we have to do. And that didn't work so well, But the cloud is amazing, the biggest computers ever built. James Hamilton, who's kind of the chief scientist for cloud at Amazon, did a paper of how many data centers do we need. And when he said, which, Amazon is a lot of legal stuff. Let's say a leading company has order 100 data centers. He didn't say how many, 100 now. Okay? How many will we need to fulfill the demand out there if all the on-premise stuff came in the cloud? He said 10,000. So we need 100 times more data centers out there. So that's a phenomenal success of what the lay person would think of supercomputers. Warehouses with 50,000 servers, 30, 60 megawatts, giant computers. But we don't think of them as supercomputers somehow. But they're up all the time. If Google search stopped, that would affect all of society, right? You go to Google and you hit search and say, sorry, it doesn't work, like all society would change. So somehow we don't classify that as a supercomputer, but it is truly successful. Supercomputers, like from the DOE and things, have been, computers for scientific computations so far, and haven't had the same interest in availability and stuff like that. So they haven't played as big a role. Because some supercomputers are using GPUs to feed their computation engine, they come along, if they buy the latest ones, they're going to have this accelerators for neural networking in it as well. So this will be kind of an interesting thing to see. Will supercomputing start used for the neural networking stuff? And will they have to worry about availability and things like that, like the cloud has? Not my fault.
Would you comment on the in-memory computing or near-memory computing in those domain-specific architectures?
Yeah, so there's people, I'm sure I bet some of those 45 startups are doing processing near memory. The Western Digital announcement was arguing kind of philosophically that they want computation near the data, so that's why they wanted the computation near the disk, so that you do processing on the disk. Micron has a design of a processor near memory there, and I think kind of the higher level statement to make about this, maybe that's my answer to Amber's question, is kind of surprisingly there's a bunch of ideas we've rejected for general purpose computing along the way, like some of the ones I've mentioned. In domain specific architecture, they don't have to do everything, right? They can just do some things well. So I think in domain-specific architectures, we could look at a lot of ideas that got rejected in the past and say, that's going to work in this case. So, a project I did with some students, the IRAM project, we did processor in memory. That could well come back in this context. So because it's domain-specific and only has to do some things well, we could see a lot of ideas make sense that don't make sense in other applications because they only have to do that one thing. So I expect to see this kind of cornucopia of architecture ideas, and that's why I think we're going to be in this renaissance of all kinds of very different things that are very different from the processors today.
So you mentioned the IE42 earlier as kind of the greatest thing.
432?
432, sorry. And I just wondered if any of those ideas have filtered down into RISC-V or is anything survived?
Close to that. There's enthusiasm in there's capabilities, there's people excited about capabilities to try and work on security. There's an effort in Cambridge, I think it's called Low Risk, and they're looking at putting capabilities back in. We actually kind of as a joke defined 128-bit architecture just because we could. And there are people who are excited about 128-bit address space. They think that that'll let them address a lot of things and put security things in there. So, and there's another capability group that I can't think of that's working on that. So yeah, there are ideas now that are starting to surface that people are interested in around capability, primarily because of the security concerns.
Okay, so I think we're already past 8 o'clock, so let's close the meeting now. And then perhaps you could, if you have any further questions, you could just follow up with the speaker offline or by email. Thank you very much.
Yes.
Okay. From other societies, if you are present here, officers, Signal Processing and Computer Society, please join us and at CIS. Please join us for final group photo, and also we have leftover tips that you could take home. Really?
Yeah, it's in the flyer.
Autonomous driving, right?
Yeah, autonomous.
Okay, yeah.
And who is your chair? I communicated with.
SSCS and the chair.
Okay.
So you can make it. I think you step down, but Paula is the chair.
Oh, sorry. I'm Yona. I'm the exiting chair for the